Okay, guys, let us start with our new lesson. This lesson is about the waves. We already started last week. We just talk about what are the waves and what are the types of waves. So today also we are proceeding the same thing. And I am just going to talk about the waves in English.
So your voice is lagging.
First of all, I discuss with what are the waves. I discussed last time. Just quick revision. I told you wave is a disturbance in a medium that transports energy. It can be mechanical wave or it can be electromagnetic. Mechanical wave need medium. Electromagnetic wave don't require medium, light wave. Mechanical wave are further divided into longitudinal wave or transverse wave. Transverse wave is one in which wave particle move up and down but wave move forward. So if wave is moving to the right, the particle will move up and down. Like I gave you the example of water and the rope, that whenever you move the wave in the rope, your hand moves up and down, the rope moves up and down, but wave moves forward. This kind of wave is called transverse wave. Transverse waves are the ripple on the surface of the water, vibration in the guitar string. Also, we discussed that the upper portion of these waves are called crust, lower portion are called trough. One crust and one trough combinedly called wavelength or crust to crust, trough to trough is called wavelength. The maximum height from crust to trough is called wavelength. The maximum height from crust is amplitude, or mean position to trough is also amplitude. So from crust to trough equal to 2 amplitude. We discuss. Secondly, we discuss about transverse wave. We sorry longitudinal wave. In longitudinal wave, yeah, as you can see in this spring, it is a slinky spring. In slinky, you can see some particle of the spring are close to each other, they are compressed, and some are expanded. So this kind of wave in which particle move forward and backward, whereas the wave move forward, this kind of wave particle of medium move parallel to the direction of propagation, like in sound waves or ultrasound wave. These are called longitudinal wave. For the case of longitudinal wave, I just want to show you another example. In the simple waves, if you guys remember, I give you few examples. Like I showed you what is wavelength, what is crust, what is trough in transverse wave. So let me check if it is possible. I can just show you one more time how can we use longitudinal wave in these terminologies. For example, this is the last week's explanation. You know, I wrote the definition of the wave: disturbance in the medium used to transport energy, then mechanical wave, electromagnetic wave. Then we talk about type of the mechanical wave. I try to show that this is a transverse wave, particle move up and down, wave forward. Then I showed you the particle move left and right, whereas the wave is moving to the right. So these are the some basic definition that we already did last week. But there is one more thing that I just want to remind you, that I told you the different terminologies. What were the terminologies? I told you the upper portion is called crust, lower portion is called trough. So the one crust and one trough is called wavelength, or trough to trough or crust to crust is also wavelength. It is denoted by lambda. Frequency, waves per unit time. Time to complete one wave is called time period. For finding the speed of the wave, we use v is equal to f lambda, or v is equal to lambda over t. So these are the terminologies that we used last time in last week's lesson. So today I am just continuing the same thing, and I am just going to talk about the longitudinal wave a little bit. If you look at this drum, someone is beating the drum. When this someone is beating the drum, the air particles near to the drum are compressed to each other. So this is called compression. When the drum surface is moving out, there is a compression. When it is moving in, there is a rarefaction. So this, as the body of the drum moves forward and backward, compression and rarefaction, compression followed by a rarefaction followed by a these compression and rarefaction start moving from source towards the listener. Now I just want to derive some terminologies. So here in this form, this portion where density is high, we call it is a compression. For example, if you see, it is written in the figure that compression is the portion where density is high. So this is the compression, and C, and this is another compression. So distance from compression to compression, from here to here, is called wavelength for the longitudinal wave. Or similarly, expansion E to the expansion E. This will also be called a wavelength lambda. So here we can also define that one compression to one compression, or one rarefaction to one rarefaction, is called a wavelength. Also, if you use the definition of the transverse wave, we can also develop longitudinal wave as a transverse wave. If you look, what is the density here? In a compression, more density. When you talk about rarefaction, here expansion, less density. So more dense and less dense waves can also be created like the transverse wave. If you look, I tried to draw the density at the position. Here y-axis is density, x-axis is position. The area of longitudinal wave which has high density here, the point where molecules are close, high density is considered as crust. Low density is considered as trough. So you can see that where is low density, it's like a trough, where is high density, it's a crust. Again, high density crust, low density trough. So if you continue from high density to low density, you can see that from high to low, the molecules are getting more density to less. So as they approach from compression to expansion, the density of the region is decreasing to expanded form. Then they go to compression, again density increases. So this wave looks like the transverse wave as this was in the longitudinal wave. So longitudinal wave and transverse wave are same, but it doesn't mean that you will say that this compression is a crust. Compression is not a crust. This is a compression, this is expansion. But compression behaves like a crust and expansion behave like a trough. So we can say that these behave like a trough. So this is the comparison between longitudinal and compression, longitudinal and transverse wave. So this was all about we took last time. But
Mr. I have a
today's lesson,
question.
yes, please.
So the darker side indicates the crust, high density.
Uh, yes, darker side, you can say it looks like the crust, high density and expanded form. The brighter side, it is expansion. Molecules are away. Low density mean it looks like a trough.
Okay, thank you, Mister.
Okay, today's topic actually was only introduction, but today's topic is about the speed of the wave. If you guys remember, I told you there is a general formula for the speed of the wave. What is that formula? How we can calculate speed of wave? To calculate the speed of wave, we have a formula. If you remember, today I just showed you a little while ago. How
V
can we calculate the speed of the wave?
V equals F
V is
مثلث
equal to F times
ثلث
lambda.
لambda أنا وصلت.
This is V is equal to F lambda. F is the frequency, lambda is the wavelength. This formula can also be written in time period like V is equal to lambda
Um,
over T. Okay. This is the formula for the speed of the any wave. This is the general formula. But if we are particularly talking about transverse wave in a card, so it has a different formula for speed of transverse wave in a cord. What do you mean by cord? Cord be a rope or it can be a string. Rope or string. In the form of transverse wave in the cord or spring, there is another formula for the speed of the wave. What is that formula? Let me write this one first, then I will explain what actually this is. The speed of the wave in a cord is calculated by V is equal to radical Ft by mu. Here V is representing, as you guys very well aware, it represents speed. Ft is representing tension in the cord. Whenever you have a cord from the both and fixed from the both, and so it is tight like guitar string. Tension in the cord, tension letter mu. We are using this mu in many forms. In friction, we studied last year. In friction, we use mu, static friction and kinetic friction in
Mister,
grade 9
can
and
you
10.
repeat?
Yes, please.
Can you repeat because you were lagging and I
Yes, I
didn't.
am. I am repeating the same thing again and again. Just listen. I know it's lagging sometime.
Mister, your
Okay.
voice is not lagging.
Yes, please.
It's not lagging for me, Mister.
It's okay because I know it might be my issue, might be your issue. So sometime it lagged. No problem for that. I will repeat everything. I was telling that the V is representing the speed, Ft is representing the tension in the cord, and mu. In previous classes we studied it is friction, but here it is not friction. This is the Latin word mu. Here it is used for mu is equal to mass per unit length. So it is representing mass of the card per unit length. What is this thing? It actually tells us that how much is the mass of the card at a unit length. So this formula number 3, we will use to find the speed of the transverse wave inside the, you can say, inside the card. So whenever a question comes related to the string or chord, we can use the first two formulas if frequency and wavelength are given, but we can also use this one if the tension and mass and length are given. Now, this is the formula that we have to remember, and just directly go to the question example 11:11. If you look at the example, it is wave along a wire. We are discussing wave along a wire. A wave whose wavelength is zero point 0.3 meter. So first of all, we have been provided by the wavelength. Okay. Secondly, a wave has the wavelength of this is traveling down in 300-meter long wire. The second length is the length of the wire, whose total mass is 15 kilogram. So we have also the mass of the wire. If the wire is under the tension of 1000 Newton, what is the speed? The first thing, what is the speed? And second thing, what is the frequency? So let me start with this question. As you guys very well aware that we need the data first. As I mentioned, data is marked here. So first of all, we have been provided by the wavelength, and wavelength is
Wavelength
0.
is 15.
0.30 meter, okay, and length is
Length is 300 meter.
very good,
And
very
mass
good.
is
Mass,
15 kilogram.
okay.
And the force is 1000 Newton.
Tension Ft is
Force
equal to
tension is
1000,
1000
okay.
Newton.
What is to find? First of all, we have to find V. So which formula you will use? Will you use V is equal to F lambda or V is equal to radical Ft over mu?
Uh, FT
We have
equals
these two
V
formulas.
equal radical,
equal
mister.
to FT.
I
Then
wrote in
radical.
the blue one.
You're lagging, Mister.
Okay.
Wait, you write and then F lambda or FT because I did.
First one I write F lambda. Second one I write Ft over mu in radical sample.
Oh,
Now,
okay.
I'm going to use the first formula. V is equal to radical tension
We,
force over mu. And you know mu is equal to m
Mister,
over
this
L.
is
I
FR
already
or
told you.
FT?
FT.
Okay.
FT. Now just substitute the values. What are your values to find speed? V is equal to what is FT?
1000
1000.
over 15 over
Mass is
100.
15. 300. You have the calculators. Do and give me the final answer for V.
I drink some water, but taste is not
What
good.
happened?
Mister, it's 2 over 9, which is 0.22222.
Are you sure? It's wrong answer. Do it again. Use
Oh,
the
Mister, it's
calculator
1, it's
wisely.
100.
Wherever I put the parentheses, use parentheses.
Yes,
Yes,
Mister, it's
please.
141.42.
Yes, this is the correct answer. 141.2 meter per second.
141.4 equals to F lambda. We
Okay.
have lambda, which is equal to zero point 0.3. We switch it to other side, so it becomes 141.4 over 0.3 equals to frequency,
Frequency and lambda is
zero
0.3.
point 0.3.
So when you divide it, what is its answer?
Let me check. 141 divided by 0.3, it's equal to, Mister, it's 470.6.
100 or 400.
470.56.
So 471 I can write. Yes.
Yes, yes.
So this is 471 hertz. Question number 41 from the exercise. This is a similar question. 4 kilogram cord is stretched between two sports 8.7 meter apart. When the sport is struck by hammer, a transverse wave travels down to the card and reaches to the other sport 0.85 second. So here they want us to find tension in the cord. So we are actually doing a little bit extra in this question. First of all, I'm just mentioning the data in the question. This is the mass, this is the length, and this is the time. Now we have the time given here and they are asking for the tension. So force of tension we can find by only one formula, that is V is equal to radical Ft by mass per unit length. Now if you look at this one, in this question mass is there, Ft is unknown, but we don't have the value of speed. Ft is unknown and speed is unknown. For the speed, you will use distance divided by the time. So here you will write speed is equal to distance over time is equal to radical Ft times L over M. You understand why I did this? Because this M over L will go on the other side, so it will Ft times L over M. Now, distance is actually the length of the string. So I can put here L over T is equal to radical Ft times L over M. Take the square on both sides, so it becomes L square over T square Ft times L over M. I need to find Ft, so this L on the other side will go and divide, and this M on the other side will multiply, so it will become L square times M over L times T square is equal to Ft. So finally, Ft is equal to L and L square cancelled, so L times M over T square. Now you have all the data. If you look at the question, you have L 8.7, M 0.4, and T 0.85. Just substitute the values. You will get L is equal to 8.7, M is 0.4. So I'm going to write 8.7 times 0.4 divided by 0.85 square. Let me check the time again. It was 0.85 second. Now just substitute the values. You will get the tension in the cord. Now please, one very important thing that I tried to show you in this question. In this question, they actually ask us for FT, but the data was little bit different. We had mass, we had length, but we also don't have velocity. So you can do velocity separately and then substitute, or directly substitute the values of distance is equal to length over time. So I just rearrange this one and then I found this relation. Yes, 4.8, it's correct. Now please, you can see as the situation changes, we can modify the formula. Actually, it is the same formula which we use, but I modify for the velocity because in the question, velocity was not given and tension is also not given. So I use the definition of velocity, distance over time, L over T, and then I. You can start from this point also. Just substitute the values here and then rearrange. That's up to you. Or rearrange first and then substitute the values. You guys can answer like this.
Thank you, Mr. See you. Bye bye.
Thank you. See you. Bye bye.